Okay, so the processor management. Hopefully, you should learn about the difference between job scheduling and process scheduling. That's a job as it comes in, we call it a job, and once it's brought into the system by the high-level scheduler, it becomes a process and then falls into the process scheduling. So this is where officially we learn that a program, the difference between a program and a process, some books call the program a job and some call the process a task. So these are interchangeable names. But generally, a program is a list of instructions stored and idle and doing nothing, not being executed. So a unit of work that has been submitted by a user to an operating system, we call it a program, but it's an inactive unit. While it becomes then a process once it's allocated memory, it's allocated CPU, and once it starts executing. It becomes an active entity, and we create a PDB for it. What does a PDB stand for? Process Control Block. And what kind of information you expect to find? One piece of information you find in a PCB. An ID for the process. Anything else? One piece of information in a PCB. Yeah?
Either its IO bound or CPU bound.
It's classified as IO or CPU bound. Anything else?
Size.
What could be in a PCB?
Size files.
It could be the priority, the size. All the information related to a process is kept in the PCB.
ID.
And when is the PCB created?
Unique ID.
Say again?
The unique ID. You create a unique ID for the unique ID for nodes.
Okay, thank you. When is the PCB created? Or where? Go on. The initial state. And where is it discarded? Where do we discard the PCB? The PCB is, what's a PCB? Anybody remember what the PCB is? It's a file. It's a data structure that's stuck into a list. You can make a list out of data structure. Like an array is a data structure. When is it discarded? That's when it's created at the new state. Just like your folder, when you join the college, first they create a file for you. And when you finish, after a couple of years, you finish, they get rid of it. They say, oh, thank God that he's gone or she's gone. So it's at the terminating state we get rid of the PCB. All right, okay, we keep going. An interrupt, guys, is a technique that's used. It's a hardware signal that suspends the execution of a program. Remember, if a program says, I need a printer, for example, and we say, no, the printer is not ready, then the program comes back again, especially if a programmer puts it in a loop. Okay, is the printer ready? And you say, no. And they say, is the printer ready? No. It keeps asking this question. And every time a program asks this question, do you know how it asks it? It's maybe about 10 lines of code that needs the CPU. So it takes the CPU to ask the question, is the printer ready? And we say no. It's like you're driving and you get to a traffic light and the engine is running and you're waiting for the traffic light and you keep looking at it, but nothing happens. The engine is running, you're wasting petrol at the traffic light because the traffic light is red. Maybe ideally the engine shouldn't be running at that state. Now they do it in most modern cars that use petrol. They switch off and then the moment you press it starts again. But anyway, So that's not a good way to keep asking the system, is the printer ready? Is the printer ready? Because every time you ask, you use the CPU to ask this question. So in all operating systems, you only ask once, is the printer ready? And if it is, you are given the printer. And if it's not, you're knocked off, you go to sleep. You don't use CPU, use nothing, you don't even breathe. You go asleep, and when the CPU becomes ready, we give it to you, we'll wake you up. And that's the system that's used in all operating systems. So it's called an interrupt. It's a hardware signal that suspends the execution of a program completely and activates the execution of the interrupt handler. So, all right, somebody asks for the printer is not ready, we knock you asleep and we call the printer handler. Come and take care of this guy, they want the printer. So they'll take a note of it, and when the printer becomes available, it will, they'll issue a signal to this guy to wake up and take the printer. Right, and then there's something else called context switching. Context switching is when the information, remember, if a process comes into the CPU and starts running, the CPU needs to know where do we start, which line code. And we give it, we say start at line 0. So start at the start of the page. And let's say it does 70 lines, and then the printer says, I need something, I need a printer. So now it's reached line number 70. So we take the process out, and when we bring it back again, how does it know, how does CPU know that, hey, we should start at line 71? That's because when we take the information, that's a process out of the CPU, we write down all the information, all the execution environment. What line number have you reached? Have you executed? If you are reading a file, what record have you read last? So we know the next one to read. So all this information is written in the PCB. That's why the PCB is important, and it goes with the process. So anytime we take a process from the CPU, we take the PCB and we'll fill all the information about it. So when we bring it back eventually, we open the PCB and move the information back into the registers. So now the CPU knows exactly what was the last thing that was done on this process. And this happened with every process. So two things happen when the CPU is switched from one process to another. If a process is running on the CPU, I say, okay, time to go. For some reason, it's either blocked or, let's say, blocked for some reason, it wants to print something or read something. So we have to take it out. But before we take it out, we need to copy all the information from the CPU into this process PCB. Right, and that goes. And the next process that comes in, we open its PCB and we read all the information from that PCB and put them into the registers, into the CPU. This is like turning the environment suitable for this new process that's coming in. Imagine this happens, say, in a hospital. Let's say this is an operating theater, and they're operating on somebody, maybe head part, they're operating in the head. They need more special equipment, special oxygen, whatever it is, X-rays at the same time, so they prepare the device. Now then they take them out, send them for a scan and say bring them back later. But while they're waiting, another patient comes in. There wants to come in that maybe wants to operate on the toe or a leg or something like that. So they have to remove all the other equipment, bring in the new equipment just for the leg and start working. For some reason they have to stop, let them go, bring them back again. But they bring back the head operation again. So they say, hold on, let's put everything the way it was. And they take that from the card that they write onto the patient. The point is you try to make the same environment when a process leaves, take like an image of what's happening now. So when we bring it back, we put everything back the way it was before it left. And that allows a process to continue executing without even knowing that it had left the CPU. Because remember, the process is asleep all the rest of the time, while it's waiting for printing, while it's in the ready queue, only when it gets here. As long as the next line is executed, it's happy. It doesn't even know it's stopped. So this process, saving all the information for the outgoing process, the process that was here, before it leaves, we copy all the information, save it onto its PCB, and go. And the next new process coming in, we take the information from its PCB and we write them into the CPU, and the CPU registers. This operation is known as context switching. So context switching is saving the information for the process leaving the CPU onto its PCB and reading the information of the coming process from its PCB and putting it onto the CPU. And that allows the CPU doesn't care who is running because everything is reset for the right suitable environment for the coming process. And before it leaves, they save everything. This context switching, guys, is a little bit slowish operation. So it's not a great thing to keep switching processes. It's not great delay, but still a delay. If we keep doing it very often, then it can cause a delay. And we can maybe do without that. So that's called context switching. Let's go back to some of the other names here. Context switching is saving a job's processing information on its PCB and reading the next job's information. Context switching occurs in all preemptive policies. Now, what's a preemptive policy? We have two types of systems that run, either a non-preemptive or a preemptive. A non-preemptive system is a system that will not forcibly take the CPU from a process or any device. So if a process goes into a CPU, and is allowed to stay here at the CPU for as long as it likes, and we never forcibly take it out, like this one here, the timeout, there's no timeout, then this is called non-preemptive system. If the system is preemptive, that means the system is allowed to forcibly take away the CPU or from a process or any other resource. That's called preemptive. So preemptive systems, this system that we use a quantum for, that's only runs if we are doing preemptive systems. Preemptive systems where we can stop a process. The system has a control, the power to interrupt a process, take the resource from it, and let it go. Guys, we'll continue and we'll finish at maybe 10 to 5 or so. Is that okay? Or do you still want to go break first and come back? And we stay till 5:30. We stay and we leave at 10 to 5. Okay, it's democratically decided. Okay. So we know what context switching is. We know the two schedulers. One is known as the job scheduler or the high-level scheduler, the one that deals with the new processes and departing processes, or the process So the high-level scheduler, what does it do? What happens there? It initiates the job based on certain criteria, whatever the criteria are. It could be CPU bound or IO bound. It puts the job in a sequence that uses all systems resources as fully as possible. That means it might send a CPU bound and an IO bound. So they'll be better at utilizing the resources. It strives to balance a mix of jobs with large IO interactions and jobs with lots of computation. That's CPU bound and IO bound. It tries to keep most system components busy most of the time. So we try and keep all the resources busy, including the CPU, of course. The process scheduler, that's the low-level one, it determines which job gets the CPU. It's the one that works between the ready queue, running, and blocked. So it takes from the ready queue the jobs that it should take the CPU, and it decides how long it will take it. It decides when processing should be interrupted. It's the one that decides, okay, I'm going to interrupt this process. It determines which queues the jobs should be going into, especially if we're using priority. We might have two jobs, high priority jobs, low priority jobs. So it decides where to put them. And it recognizes when a job has concluded and finished and or needs to be terminated. It's just a way of explaining what CPU-bound job and what IO-bound job. A CPU-bound job needs a lot of CPU, very little IO. A lot of CPU, a lot of little IO. The IO-bound job needs a lot of input-output and very little CPU. So it's nice for them to work together, because this will be using the CPU most of the time. When it doesn't need it, this one can use it for a little bit of time. Then this one uses it, and when it doesn't need it, this guy uses it. So the CPU is kept busy all the time. Similarly, with the I/O, let's say this is a printer. This one only needs it for a little bit. When this one is not used, it can use it. So both programs are happy, and all resources are kept busy. And that's another one measure of how efficient an operating system. They call it the utilization. How much is the CPU being utilized? That means what percentage of time has it been used? Like 90% would be a good utilization if it was 90% used. It's like if somebody buys a bus and decides to run a business, say from here to Cork or Belfast. So if your bus is utilized, highly utilized, that means 90% of the seats are busy, that means you're earning more money. If every time it goes, it's only 25% capacity is used, that means you're losing money. So in all systems, they're always looking for maximum utilization. And that's another factor you need to know about it. Utilization, the rate of utilization of resources, as well as turnaround time and average turnaround time. They are all factors that are used to maybe evaluate which system is better. Let's measure the either utilization or all of them. And so these are the status or the states of a process: the new state or holding state, ready state, running, blocked or waiting, and ending or terminating or finished state. And remember, those two here are managed by the high-level scheduler, and those three here are managed by the low-level scheduler. That's just part of the processor manager, splits itself into two parts. And this is a more kind of diagram that what we've seen. A process comes in new, it's given priority, it's given ID, it's given process control block, and it's put into the ready queue waiting to be moved to the CPU when the CPU is ready. When it's at the CPU, it has three options. Finishes, normally it goes terminating, needs I/O, it comes to the blocked state, depending on the queue for whichever I/O, or it doesn't finish and doesn't need I/O. just keeps using the CPU. It exceeds the quantum, then it's interrupted and moved back to the ready queue. So this is a PCB, kind of another way of looking at it. It's a data structure, controls process identification, process ID, process status, process state. The state is one of those states that we went through earlier. And accounting information as how long did it use the CPU, how long did it stay waiting. This is some of the information that you might find in a PCB. Identifier number, that's important. The state, is it new, ready, running, or blocked? Program counter, that's which line code have we reached so far in the CPU. So when we bring it back, we start at that line number. Memory limits, if there are any memory limits. Open files, what files are open, and what records you've read in each file, and so on. It's another diagram that shows pretty much the same, cycling around the states of a process. CPU utilization, yeah?
Where is PCB stored? Is it stored in main memory or in
What?
processor?
The PCB,
Yeah.
it's in main memory. It stays in main memory until the process finished. And all the information taken from it written to a hard disk for a log, for our own later on investigation maybe, or information, and then it's just destroyed in memory. Just like an array. You book an array for a while, and when you finish, the array is taken back by the memory manager. So before this PCB is created, we ask the memory manager, can we have a small space for that? Okay, so CPU utilization is a percentage of time a CPU is used, or the percentage of time it was not used. It's a ratio between the use of a resource and total possible use. That means the CPU was used for maybe, say, 9 seconds, could have been used for 10 seconds. That's the ratio between how much it was used or what's the total that could have been used. Throughput is a new definition. Throughput is the total or the amount of work completed in a unit time. The unit time could be minute, hour, day. For example, the throughput of programs, how many programs did we execute in the last, say, day, 12 hours or something like that. So that can be measured. If we can change few things, then throughput improves. It's like a throughput of a car, say, car factory produces, say, 10 cars a day. That's the throughput per day. So the throughput is the total amount of work done according to that particular industry in a unit time. Again, the unit time is different from one industry to another. Car manufacturers probably talk about a day, how many cars we produced a day. Here, we probably talk about how many processes have we executed today. So throughput is the amount of time, amount of work completed in a unit time. In other words, throughput is the process is executed or number of jobs completed in a unit time. Could be an hour, could be a day. The scheduling algorithm must look to maximize the number of jobs. So if you set your quantum to a certain level and run your programs today in a company, and you run 500 programs, and tomorrow you modify it and you run 700 programs, then you say, oh, the new setting is better. You might be actually change certain parameters in order to improve production. Throughput is the total amount of work done in a period of time. Response time We've talked about those as well. Response time is the time taken to start producing some negotiable reaction to a request. Some reaction. Response time is the time from the moment you say run this program until you see something as a reaction to the running of the program. Maybe the screen clears. That's the first thing that the program does. That's until that point, that's the reaction time or response time. Turnaround time is from the initial starting time until the completion. Turnaround time refers to the time between the moment of submission of a job and the time of its completion. That's called turnaround time. Waiting time. Anybody remembers waiting time? It's the time spent waiting on the CPU, not waiting on a printer, only on the CPU. That's the process that's called ready. Should have been called waiting, but they used to call the other one waiting, so that gave always conflicting information. But the waiting time is waiting for the CPU. That means you are ready to run. All you need is the CPU. You have everything else, but you still will not run because the CPU is not available. So that's something we try to minimize for every program. We try to minimize. Turnaround time, we try to minimize. So if you run the system in one setting that gives you turnaround time or an average turnaround time, and you run it in a different setting, give you different turnaround time, the one that gives the smaller turnaround time is the better. And the same with the waiting time. Fairness. Sometimes we always favor the smaller processes. They'll give us better performance and less average turnaround time. But it's not fair on them. Well, no, it's not fair on the larger one because we keep pushing the larger processes away. We put them back in the queue. So sometimes there's a conflict between getting better performance and being fair. But that's okay. Sometimes not being fair is better for the system. So the next one, the last thing that we'll finish it next week, it's called the scheduling policies. That how does the scheduler, the low-level scheduler, schedules jobs? Which way is the best way to schedule them? For example, if the resources are limited and you need more processes need them, which one would you give which to which? So you need to do whichever technique that will give the following results. You want to maximize the throughput. You want to that's increase the production. Do more work. Get more processes executed per day, for example. You want to minimize the response time. You want quick response time. You also want to minimize turnaround time. Every process comes in, we'd like it to wait for, get the total time from submission to execution, we'd like it to be short because it doesn't have to wait so long in the queue. Remember, it will go around many times into the ready queue and the ready state. And the longer it's spent in the ready state, that increases the turnaround time. So we want to minimize turnaround time. We want to minimize waiting time in waiting for the CPU in the ready queue. We want to maximize CPU utilization. We want the CPU to be utilized most of the time running. We don't want it to be, sitting idle. And if you do a lot of context switching, that will, while you're context switching, while a process is being taken away from the CPU, and the CPU is being prepared for the next process, that's what we call context switching, that takes certain length of time. We don't want to do thousands of this, because that means that CPU is going to be sitting idle for that length of time. And so that means if the CPU is not working, the utilization drops. of the CPU, and ensure fairness for all jobs by giving everyone an equal amount of CPU or I/O time if possible. All right, turnaround time. Again, turnaround time, response time, waiting time, throughput. So these terminologies you could be asked in the exam. Last year, like there were 3 or 4 of those, define those. And so you need to know them. And they are kind of, take them logically, you'd remember them. Right, remember that there are 2 kinds of policies or systems that we can use. A preemptive or non-preemptive. Anybody remembers the difference between preemptive and non-preemptive? Anybody can remind us? What's a preemptive system? Yeah? Pardon? So a system where we can interrupt the process and take the CPU from it without its permission, kind of thing. So that's called, what's that called? A preemptive system. And what's a non-preemptive system? The idea what a non-preemptive system is? Yeah, I know.
You need permission to stop.
So when a CPU cannot be taken away from a process without its permission. And what's turnaround time? The idea what turnaround time is? It's the total time from submission until termination, until finishing time. That's called turnaround time. What's the response time? The idea of response time is? Somebody's answering there. Yeah. Okay, okay. The gentleman. Who was it? Yeah. It's not very clear. What's the response time? It's not related really to input and output. Response time. Anybody knows what response time is? Until it shows something. Once from the time from you starting the execution of a program, until you see something as a reaction to that. Any sign that the program is running. Yeah, that's okay. But I think it's the time from initiation of a program until you see some sign that as a response to this action. Sometimes the program clears the screen. Okay, the moment it clears the screen, I know that the program started running. Or it displays some image. I know once I run this program, it probably displays some image. The moment I see the image, I say, okay, that's the response. It hasn't finished running. Response time just so you know it's actually has made some kind of response. If I say display the list of students' names, this is a good example. From the moment you say run this program, show me the list of 100 students, and the moment it shows the first name, that's the response time. From the moment starting until you see the first name. And what's the turnaround time? From starting until you see the end of the list. So that's response time and turnaround time. All right, that's what we'll be doing next week, but these are the type of processes. So first, let's go with non-preemptive. That means we're not going to interrupt anybody. There's no quantum in this case. If you get the CPU, you keep it until you give it up or you finish. Okay. This is the first come, first served. How long we want to work out? What's the average turnaround time? You have 3 jobs, guys. Job A, job B, job C. Job A needs 15 milliseconds, or 15 seconds, or 15 unit time, whatever it is. and job B needs 2 milliseconds and job C needs 1 millisecond. Let's say they arrived in this order, but they're all there now at time 0. So we want to execute them. And we are running first come, first served. That means the first job that arrived first, we'll give it the CPU first, without any preemption. We'll never interrupt anybody. We give it for as long as it needs. So job A gets the CPU first because it arrived first. It starts at time 0, it runs for 15 milliseconds, finishes. What's the turnaround time for A? What's the total turnaround time for A for this process? It started at 0, it finished at 15. The total turnaround 15 minus 0, 15. Now, job number B and C, they're all waiting here. But they had to wait for 15 milliseconds, and the next one we give the CPU to B. B needs it for 2 milliseconds. So it finishes at time 17. What's the total turnaround? What's the turnaround time for B? Started at 0, finished at 17. Not 2 seconds, 17 seconds. And C was waiting from time 0, and now it gets the CPU for 1 millisecond, finished at time 18. So what's the average turnaround time? Average. This is an important measurement, the average turnaround time. So for A, it took 15 seconds, plus B took 17, and A 18. So 15 plus 17 plus 18, and divide them by 3. And we get 16.67 seconds or milliseconds or whatever the unit time. So that's how to calculate the average turnaround time using first come, first served in non-preemptive system. This is an easy system to implement. First in, first out is always easy to program. But let's imagine this is because the jobs arrived in this order. Imagine if the jobs arrived in a reverse order. So we are really depending on which job comes in first. So in this case, let's say job C arrived first, and then B, and then C. Now they're all sitting here at time 0. Who gets the job first? Job C got it first. So it arrived before B and A. It got into the queue first. So it starts running, finishes after 1 second. What's the average? What's the turnaround time for C? 1 second. B is waiting at time 0, waiting for 1 second. Now it gets its turn. It finishes at time 3. Starts at 0, finishes at 3. You always need to find out what's the turnaround for each job. And then A was waiting for 3 seconds and then ran for 15, finished at time 18. What's the average turnaround time now? 1 plus 3 plus 18 divided by 3. These are exactly the same jobs. We just changed the order in how to execute them. And it changed the turnaround time from the previous one. Oh. Where did I go? From 16.67 as average turnaround time into 7.3. That's more than 50% reduction in the average turnaround time. Imagine you go to a supermarket, you spend 15 minutes on average. Imagine if we can cut that down to 7 minutes. That's a huge amount of saving if we can do it. And that's an average. That means everybody on average, most people are going to get a reduction in time. So that's in this system, they used to be on average 16.6, and now they're average 7.3, just because we changed the order. We brought the smaller jobs first. So always remember, first in, first out, easy to program, but sometimes give us good results, sometimes gives us poor results because we don't control who comes in first. The next one, if we intentionally say, no, from now on, the shorter job is going to go in first. This always gives the best performance, gives the best average turnaround job. We tried the example earlier on. This is the shortest job next. Again, non-preemptive. We've already had an example. Here's another example. Let's say these jobs are available right now. They're all available. I don't know. Yeah. We look at them, we say, who's the shortest job? B. So we start with B. Let B run for 2 seconds. And then D is the next one. If we knew how long, the problem with this, you need to know in advance how long would a process take to execute. It's not always easy to try to do that. Sometimes the size of the code, you know, how many lines of code you have, but that's not always a perfect indication. Because sometimes somebody has a short program but has a lot of loops inside it. It'll take a lot longer than even a longer program to execute. Do you know what I mean? So if you've started programming. So now anyway, the next job after D is A because it takes 5 milliseconds. And then finally, the longest job, C. Now if you work out this, the average turnaround. B finished at time 2. D started at 0, finished at 6. So the turnaround is 6. We write down here the turnaround for that job. From whenever it came in. They all came in at time 0. Sometimes you get examples where, no, D didn't come at time 0, it arrived at time 7. From somewhere here to there, for example. But anyway, so this is the average turnaround here using the shortest job next, and it gave us 9 milliseconds. So these are the kind of examples you might get in a test or in an exam. You're told is calculate the average turnaround time using the shortest job next, or first come, first served next. Or you could be asked, which one would give us better results? In this case, we have those 3 jobs. They arrived in this order, A, B, C, D. Is it better to, you know, which one would be better? Shortest job next to first come, first served. And you have to do both examples and say this one gives better results. Smaller average turnaround time. So this is another example of a number of processes. They arrived at different times. They're not all there at time 0. If you are told process number 1 arrived at time 2, while process 2 arrived at time 0, so that arrived first. And then those, and then that one, and that one. And this is the length of time they all need the CPU for. They're called burst times or CPU time. So you need to draw a Gantt chart where it starts showing all the time from time 0 to the maximum time. Which one arrived first? For example, process number 2 arrived at time 0. What time did it finish? It needs the CPU for 1 second. So it finished at 1 second. Right, the next thing, from 1 to 2, there is no CPU used. And no processes, but 1 and 3 arrived at time 2. Process 1 and process 3. Okay. So process 1 arrived at 2, and it had 2 burst times, that means 2 CPU times, it finished at 4. Process number 3 arrived at the same time, 2, and had to wait for 2 and then run for 3 seconds. So it will finish at this time. Are you able to see this? Remember, CPU can only run 1 program, and this is non-preemptive. So 2 and 3 arrived at this time. No, 1 and 3 arrived at this time, but 1 started running. It's run for 2 seconds. So 3 could have run, but it can't run while 1 is running. So 1 finishes here, number 3 starts running, and it needs to run for 3 unit time, so it finishes at 7. Even though process 4 arrived at this time here, at time 3, but the CPU has been busy up until 7, so it only starts at 7 now. So you need to know from this point until this time, That's the total turnaround for process 4. So 4 started running at 7 until 12, but it actually arrived at time 3. Guys, stop talking, please. All right, so these are the times when they ran and finished, but not when they arrived. So now, what I want to calculate here, when is the completion time? When is how much is the turnaround time? How much is the waiting time? And how much response time? I'll leave the response time. So, who's going to do this for the first process? Process number 2. Or process number 1. Okay. Will I pick or will I see hands going up? You look like you are comfortable enough to tell me. Yes. Process number 2. Or sorry, number 1. It arrived at time 2 and it needs CPU for 2 seconds.
Completion time is 4.
Where's completion time? What time did it finish?
Time 4. If it arrived at 2 and where's the time?
Okay, sorry, it's process 1. I was looking at process 2 for you. Yeah, so it finished at time 4. What's the turnaround time?
2.
It arrived at time 2, finished at time 4, finished at time 4, 4 minus 2, so the turnaround time is 2. Right, and what's the waiting time? Did it have to wait? No. No, it didn't. Arrived time 2, and it waited for 0 length of time. Okay, let's go to the next one. Process number 2. Yeah. Process number 2. It arrived at time 0, it finished at time 1.
Completion time is 1.
Oh no, it didn't finish at time 1, I don't know. It needs the CPU for 1 second. It finished at time 1. So, what's the completion time?
1.
1. What's the turnaround time? 1 minus 0 is 1, yeah. And waiting time? 0. Okay, next one. Any hands going up there? Yeah, I see your hand is moving, yes? Go on. Process number 3. What time did it finish at? 7. And what time? It's turnaround time. 7 minus, when did it arrive? It arrived at time 2, so 7 minus 2 is 5, yeah? Perfect. And waiting time? It arrived at 2, but it didn't start running until 4. So it waited for 2 seconds. Yeah. Right, process number 4. Who's gonna do it? What? Where? Process number 3. What's wrong with it? It arrived at time 2. Here's process 3. It arrived at time 2. It finished at time 7. So turnaround is 7 minus 2. You okay? All right, go on. Number 4. Completion time is 12. Yeah, okay.
Turnaround time 5.
From the time it arrived, 12. What's turnaround time?
9.
From the time it's arrived until the time it finished. What time did it arrive at? Arrived at time 3.
Yeah.
And it finished at time
12.
12. So 12 minus 3 is 9. Yeah. Anything else? Waiting time. It arrived, it started running at time 7, but it arrived at time 3. So from 3 to 7 it wasn't running. It arrived at 3, but it had to wait. So 4 is waiting time. Anybody from the back there? Anybody following us? Yeah, go on. Process 5. Completion time 16, yeah. So process 5 finished here at time 16. It started at time, arrived at time 4. What's the total turnaround? Yeah, yeah, finished this, right, at 12, so that's 16, 12. Waiting time, it arrived at time 4, but it started running at time 12. So it was waiting for 8. Okay, so it's a piece of cake, right? Until you start doing it, and then it gets a little bit more complicated. Priority is another thing. Okay, tell me when we get to quarter 2. So priority is sometimes a job is more important than another job, and it gets ahead of it. It's easy to implement. And if the priority is similar, for example, we have 2 types of processes, important and not important, or priority 1, priority 2, that's all. So if we have multiple priority 1s, which one would you pick? You pick the one that came in first. So in the case of equal priority, we go for the first in, first out. Now this is where it gets a little bit complicated. The preemptive jobs. This is the preemptive version of shortest job next. So shortest job next we looked at, the short job comes in, we let it use the CPU first. But we don't interrupt it anymore. Even if another shorter job comes in afterwards, while this one is still running, we don't interrupt it. But in a preemptive system, if we say this is preemptive, guys, for shortest job, that means as long as the job is shorter, we'll give it the CPU. Let's say a job is 5. It's the shortest in all the other jobs. So we say, okay, you can run. So it starts running, 5. Got 4 seconds left. And then a job comes in that only needs 2 seconds. Now that's shorter than the one that's running. This is a preemptive. We interrupt the one that's running because of higher priority, better priority. When you say higher priority, that means lower number, for example. But more important, it's easier to say, a more important job comes in, then we interrupt the one that's running. If it was priority with non-preemptive, that means if you have the shortest job, you start first. But once you start, even if you get another job comes in, we don't interrupt you because this is a non-interruptive system. But if it's a preemptive system, that means, yes, we could interrupt you even if you get... This is like you going to fly in an airplane, right? And you have no booking. You have no booking. The airplane is fully booked. So usually the airplane, if 5 people don't arrive for their flight, the airlines doesn't want to lose the money, so they take passengers who don't have booking. But they keep it till the last 10 minutes before the flight takes off. If passengers with booking do not arrive, then they have free seat. They give you a seat and they call you standby passenger, but they give you that seat. Imagine they give you the seat and you're happy, you're running in the plane, and you sit on the seat and that passenger arrives that had booked that seat. Would they take you off? Or that's it once you got the seat? If it's preemptive, they will take you off. If it's non-preemptive, no. Once you get your seat, once you get the boarding pass, they'll never take you off. Especially if the airplane takes off. You don't want to be removed off the flight. So always think of preemptive and non-preemptive. In preemptive, you can be interrupted. Even if you are running, you could be stopped. So let's look at this example of preemptive shortest job. Okay, watch this, guys. This is it. This is the hardest thing. This is the most difficult, complicated kind of thing. So imagine we have a time 0, time 1, time 2, and 3. We have 4 jobs that arrived. A arrived the first, then B, then C, then D. They arrived at different times. So we know when each one arrived. And A needs 6 time units, B needs 3, C 1s, and all that. So let's look at this. Time 0, A arrived. No one else is in the system. So A starts running. There is no other job in the system. It's the only job. After 1 second, job B arrives. Now A needs 5 more, but B needs 3. This is a preemptive system for shortest job. So A is interrupted. We say, sorry, stop. But remember, it only needs 5 now. And B is given the processor. B starts running. After 1 second, C arrives. After 1 second, say, hold on, C is shorter, is it? B is shorter. B starts at 3, but now it only needs 2 more seconds. This one only needs 1, that's shorter. Stop B and give the processor to C. So C starts running for 1 second and finishes. It finishes, who's there? A, B, and D. But A is 5, B is 2, D is 4. B is the shortest, so we give the CPU to B. So B runs for 2 seconds, finishes. There are only D and A. A is 5, remember 5 because it's run 1, and D is 4, so we give the CPU to D, finishes after 4, and then we give A. This is called preemptive, shortest job first. What's the average turnaround time here? What's the average turnaround for A? What's the turnaround time? What's the definition? What's turnaround time? From arriving into the system until leaving the system. What time did A arrive and what time did it leave?
0 and 1.
It arrived at time 0 and finished at time 14. The rest of the time it was waiting inside the system doing nothing. So the turnaround time for A is 14. What about B? Anybody there in that line? Yeah? Yeah? Go on. Okay, anybody? Next line. How about you? B. What's the, turnaround time for B? What time did B arrive at?
No. 3.
Arrived at time 1 up at the top. And what time did it finish at?
5.
B finished at time 5. So from 1 to 5, 4 is the turnaround time. Right, what about C?
Yeah, 1 to 1 turnaround.
It arrived at time 2 and finished at time 3, so the turnaround is 1. Anybody here? Yeah, go on.
D is
D, the
starting
next
from
one.
5 and finishes at 9, so it's 1.
So D arrived at what time?
5.
No, it started running at 5, it didn't arrive at 5.
It arrived at 3.
Yeah, so it arrived at this time and finished at this time, I guess, 9. So what? 6, yeah. So 6 is the turnaround time. The finishing time minus arriving time. So the turnaround time includes the waiting time, guys. All the runnings and all that. Okay, so that's really the hardest thing. If you can manage that, there's no problem after that. This is exactly the same jobs. This is the same job, shortest remaining time. Oh, is this shortest remaining time? Yeah. This is shortest remaining time. Shortest remaining time, but it's non-preemptive. It's the same example, the same processes, same numbers. Remember the last one we've done? The average turnaround is 6.25. See, the averages, turnaround times are written up there, and this is the average, 6.25. Now then, this is the same jobs, but it's not preemptive, non-preemptive. That means we will not interrupt you. If you're running on the CPU, we won't interrupt you. We want the shortest job. But once the shortest job starts running, it doesn't matter if other shorter jobs come in. We will not interrupt it. That's non-preemptive. So let's start running. 6 starts running. 1 second later, B arrives. It's shorter than 6, but shorter than A. But A is already running. This we cannot interrupt it. This is non-preemptive. And then, well, by the time A finishes at time 6, those 3 are here. C is the shortest, and then B, and then D. When we work out the average turnaround time in non-preemptive, we get 7.75 seconds. The previous one, when we did the preemption, it gave us 6.25. So really, the ones that give the best performance possible are the shortest jobs with preemptiveness. They would give the best performance. So we'll finish the rest of it next week. Well, not next week, the following week. Next week is an assignment week. There are no lectures. I'll be putting a tutorial. You'll need to go through it and answer it. Attend it.